coordinates, except instead of r, I'm using u, and instead of theta, I'm using v. Okay. Y is u sine v, and then z is the square root of x squared plus y squared. That's just going to be, well, what is it going to be? What?
I looked at the notes, so I don't count.
Okay. What? Yeah, it's just going to be u. Because you have u cosine squared plus u sine squared. And then u is going to be between 0 and 1. V will go from 0 to 2 pi. All right. So now it's.
Now you know u goes. Oh, I figured it out.
Okay. Yeah. From. Yeah. Okay. And because we're going all the way around, v will go from 0 to 2 pi. So from this point, it's fairly straightforward, actually, believe it or not. So we compute these vectors, partial derivatives with respect to u. So it's kind of like the last example, but not exactly. Sine v1. So we have minus u sine v, u cosine v, 0. So then when we compute the cross product, we're going to have minus u cosine v. Then we're going to have minus u sine v. And then we have u cosine squared plus u sine squared. So that's just going to be u. I'm going to factor out a u here for convenience. So we have minus cosine v, minus sine v, and u. All right.
Factor out the u, should that be a 1?
What?
Since you factored out the u, should that not be a 1?
Oh, yes, it should be a 1. Okay. Now, so now if we take a look at this normal vector that we get, notice that no matter what, since u goes between 0 and 1, the z component of a normal vector is going to be at least non-negative. It's going to be positive everywhere except right here at the point of a cone. So we get a normal vector that's pointing like this, at least in this direction. All right. Now, because we have that positive z component, this is called upward orientation. Whereas you can flip the normal vector, so it's still perpendicular to the surface at each point. So this is downward. Orientation. All right. So now, typically a problem is going to specify which orientation you're supposed to use. In this case, the problem, as given in text, specifies downward orientation, which means that so the downward normal is just simply the negative of this. So we're going to have u cosine v sine v minus 1. So that's the downward pointing normal. Now, after an example, I'll say more generally how you compute the, how to keep the orientation straight for any surface that's a graph of a function of two variables. So there's a straightforward way of doing that. Basically, you look at the z component. Because for such functions, such surfaces, the z component is going to be very simple. Easy to tell what sign it is. Okay. So if you get the orientation wrong, that means your integral is just going to have the wrong sign. Okay. Okay, so now we're going to set up the surface integral. So the surface integral of f dot ds. So we're going to integrate over parameter space, so from 0 to 1 in u, and 0 to 2 pi in v. And we're going to have our vector field, x, y, z to the fourth, dot product with u cosine v, sine v, and minus 1, du dv. But I need to write x, y, and z to the fourth in terms of u and v. So you go to your parameterization and fill that in. So we have u cosine v, u sine v, and then z to the fourth, that's u to the fourth. Dot product with u times cosine v, sine v, minus 1, du dv. So we work out the dot product. We have a u sitting out here, this u, and then I'll work it out everything else. U cosine squared v plus u sine squared v, that's going to be u squared, minus u to the fourth, du dv. So I love allergy season in Mississippi. And yes, it is way worse than any other state I've lived in. So we get u cubed minus u to the fifth. Oh, wait.
There's a discrepancy
Yeah.
somewhere with what you have.
Yeah, here I have u cosine squared plus u sine squared. So this should only be a u. So then I have, once I put in the other u, I get u squared minus u to the fifth, du dv. Okay. All right. Now, we have no dependence on v whatsoever. So, when we integrate, we can, because of that, we can actually pull everything with respect to u out. We really have integral from 0 to 1, u squared minus u to the fifth du, times integral from 0 to 2 pi times 1 dv. So when the integrand separates very nicely like that, or if it only depends on one variable at all, that's something you could do. So this integral is just going to be 2 pi. So we'll have 2 pi, then we have u cubed over 3 minus u6 over 6 from 0 to 1. So we get pi over 3. Okay, so you compute your cross product. At that point is when you check, do you have the orientation that's required, upward or downward? And then, so the problem is meant to supposed to specify what orientation you should be using. Then you put in this cross product here to take the dot product with a vector field. The vector field, this is f with your parameterization plugged in. So you work out the dot product, and then you are ready to integrate. All right. Now, the other way to do this is at the outset to leave everything in terms of x, y, and z, not go to polar coordinates or cylindrical coordinates right away. Because in that case, well, first, any questions about what's up here before I talk about graphs of functions? Because that's sort of a special case. Not all surface integrals are going to involve a surface defined like this. So